Okay, folks, today is almost the last day of this whole get back in the habit of more intense coding. I'm going to be taking a step back, and I think I'm just going to go through a visualization course. I have my book on this, but I'm wondering if because it's about how code moves, I need to look at it more visually. So this is a highly recommended course from 2019, 6 million views. And it goes from easy concepts to more advanced data structure concepts. And that's kind of what we're talking about here. It's going to go through pretty much, we're going to stop somewhere in here, but it goes all the way up. And we might actually go all the way through the binary searches before we get to hash tabling. But that's where we are. That's what we're doing today. You're welcome to watch me watch this or to watch it by yourself. So yeah.
Videos, I want to lay the foundation of some core concepts you will need throughout these video tutorials. Let's get started with the basics. So what is a data structure?
Hold on.
It is a way of organizing data in some fashion so that later on it can be accessed, queried, or perhaps even updated quickly and easily. So why data structures? Why are they important? Well, they are essential ingredients in creating fast and powerful algorithms. Another good reason might be that they help us manage and organize our data in a very natural way. And this last point is more of my own making, and it's that it makes code cleaner and easier to understand. As a side note, one of the major distinctions that I have noticed from bad, mediocre to excellent programmers is that the ones who really excel are the ones who fundamentally understand how and when to use the appropriate data structure for the task they're trying to finish. Data structures can make the difference between having an okay product and an outstanding one. It's no wonder that every computer science undergraduate student is required to take a course in data structures. It is strange that before we even begin talking about data structures, that we need to talk about the abstraction of data structures. What I'm talking about is the concept of an abstract data type. What is an abstract data type, and how does it differ from a data structure? Well, the answer is that an abstract data type is an abstraction of a data structure which provides only the interface to which that data structure must adhere to. The interface does not give any specific details on how a specific data structure should be implemented or in what programming language. One particular example I like to give is to suppose that your abstract data type is for a mode of transportation to get from point A to point B. Well, as we both know, there are many modes of transportation to get from one place to another. So which one do you choose? Some specific modes of transportation might be walking or biking, perhaps even taking a train, and so on. These specific modes of transportation would be analogous to the data structures themselves. We wanted to get from one place to another through some mode of transportation. That was our abstract data type. How did we do that exactly? Well, that is the data structure. Here are some examples of abstract data types on the left and some possible underlying implementation on the right-hand side. As you can see, a list can be implemented in two ways. You can have a dynamic array or a linked list. They both provide ways of adding, removing, and indexing elements in the list. Next, we have a queue and the map, abstract data types, which themselves can be implemented in a variety of ways. Notice that under the implementation for a queue, I put a stack-based queue because, yes, you can have a queue which is implemented using only stacks. This may not be the most efficient way of implementing a queue, but it does work and it is possible. The point here is that the abstract data type only defines how a data structure should behave and what methods it should have, but not the details surrounding how those methods are implemented.
If you have a love of languages, you may want to consider a career in the Navy.
As a cryptologic technician interpreter.
All right, now that we're done with abstract data types, we need to have a quick look at the wild world of computational complexity to understand the performance that our data structures are providing. So as programmers, we often find ourselves asking the same two questions over and over and over again. That is, how much time does this algorithm need to finish? And also, how much space does this algorithm need for my computation? So if your program takes a lifetime of the universe to finish, then it's no good. Similarly, if your program runs in constant time, but requires a space equal to the sum of all the bytes of all the files on the internet, your algorithm is also useless.
Yep.
So to standardize a way of talking about how much time and how much space is required for an algorithm to run, theoretical computer scientists have invented big O notation, amongst other things like big theta, big omega, and so on. But we're interested in big O because it tells us about the worst case. Big O notation only cares about the worst case. So if your algorithm sorts numbers, imagine the input is the worst possible arrangement of numbers for your particular sorting algorithm. Or as a concrete example, suppose you have an unordered list of unique numbers, and you're searching for the number 7, or the position where 7 occurs in your list. Then the worst case isn't when 7 is at the beginning or in the middle of the list. It's when 7 is the very last element of the list. For that particular example, the time complexity would be linear with respect to the number of elements in the size of your list, because you have to traverse every single element until you find 7. The same concept applies to space. You could just consider the worst possible amount of space your algorithm is going to need for that particular input. There's also the fact that big O really only cares about what happens when your input becomes arbitrarily large. We're not interested in what happens when the input is small. For this reason, you'll see that we ignore things like constants and multiplicative factors. So in our big O notation, you'll often see these coming up again and again and again. So to clarify one thing, when I say n is usually always going to be the input size coming into your algorithm. There's always going to be some limitation of size n. So constant time we refer to as a 1 wrapped around a big O. If your algorithm takes a logarithmic amount of time to finish, we say that's big O of log of n. If it's linear, then we just say n. If it takes like quadratic time or cubic time, then we say that's n raised to that power. If it's exponential, usually this is going to be something like 2 to the n, 3 to the n, any number b greater than 1 to the n, and then we also have n factorial. But we also have things in between these, like square root of n, log of n, n to the 5th, and so on. Actually, almost any mathematical expression containing n can be wrapped around a big O, and is big O notation valid. So now we want to talk about some properties of big O. So to reiterate what we just saw in the last 2 slides, big O only really cares about what happens when input becomes really big. So we're not interested when n is small, only what happens when n goes to infinity. So this is how and why we get the first 2 properties. The first, that we can simply remove constant values added to our big O notation, because if you're adding a constant to infinity, well, that's just infinity. Or if you're multiplying a constant by infinity, yeah, that's still infinity.
It is still
So we can ignore constants. But of course, this is all theoretical. In the real world, if your constant is of size 2 billion, yeah, probably that's going to have a substantial impact on the running time of your algorithm. However, let us look at a function f, which I've defined over some input size n. If f of n is 7 log of n cubed plus 15n squared plus 2n cubed plus 8, well, big O of f of n is just n cubed, because n cubed is the biggest, most dominant term in this function. All right, now let's look at some concrete examples of how big O is used. So both of the following run in constant time with respect to the input size n, because they don't depend on n at all. So on the left, when we're just adding or doing some mathematical formula, yes, that's constant time. And on the right, okay, we're doing a loop, but the loop itself doesn't depend on n, so it runs also in a constant amount of time. So as our input size gets arbitrarily large, well, that loop is still going to run in the same amount of time, regardless. Now let's look at a linear example. So both the following actually run in linear time with respect to the input size n, because we do a constant amount of work n times. So on the left, we're incrementing the counter I by 1 each time. So f of n is n, and clearly when we wrap this in a big O, we get big O of n. On the right, a little bit more complicated, we're not incrementing by 1, we're incrementing by 3. So we're going to finish that loop 3 times faster, so f of n is n over 3. So our second example is 2 algorithms that run in quadratic time. So the first one seems obvious. We do n work n times, so n times n is big O of n squared. But observe the second one. I changed the 0 with an I. So pause the video and try to figure out maybe why that's big O of n squared. Okay, let's go over the solution. So first, just focus on the second loop. The first loop isn't as important. So since I goes from 0 to n, the amount of looping done is going to be directly related to what I is. And remember, I is changing from the outer loop. So if we fix I to be 0, we do n work. If we fix I to be 1, we do n minus 1 work. If we fix I to be 2, we do n minus 2 work, and etc. So the question then becomes, what is n plus n minus 1 plus n minus 2 plus n minus 3, and so on? Well, this is a well-known identity, and it turns out to be n times n plus 1 divided by 2. So if we wrap this in a big O, we split our equation, we can see that this is big O of n squared. Now let's look at perhaps a more complicated example. Earlier, you may have wondering, how do we ever get these logarithmic or linear rhythmic time complexities? So here's a classic algorithm of doing a binary search, which yields actually a logarithmic time complexity. So what this algorithm does is it starts by making 2 point errors, one at the very start and one at the very end of the array. Then it selects a midpoint between the two and checks if the value we're looking for was found at the midpoint. And then it has either found it or not. If it has found it, it stops. Otherwise, it discards one half of the array and adjusts either the high or the low pointer. Remark that even in the worst case, we're still discarding half of the array each iteration. So very, very quickly, we're going to run out of array to check. So if you do the math, the worst case is you will do exactly log base 2 of n iterations, meaning that the binary search, well, runs in logarithmic time. A very cool algorithm, a very powerful algorithm. Here's a slightly different example worth going over. So first, notice that there is an outer loop with a counter I that does n work. Then notice that there are 2 inner loops, one that does 3n work and another one that does 2n work. So the rule we use to determine the complexity of this algorithm is to multiply loops on different levels and add those that are the same, generally speaking. So using the rule above, we can see that it takes n work to do the outer loop, multiplied by 3n plus 2n for both inner loops, which gives us 5n squared, which is big O of n squared. All right, so this next one looks very similar, but it's actually quite different. So on the outer loop with I, we have I going from 0 to 3n. So there's 3n work done on the outside. But we have to multiply that by what's going on the inside. So on the inside, j goes from 10 to 50. So that does 40 loops, exactly, every loop. So that's a constant 40 amount of work. Plus, however, the second loop. So j is less than n cubed, but j equals j plus 2, so it's accelerated a little. So we're going to finish that loop a little faster. So we're going to get, on the inside, 40 plus n cubed divided by 2, but we have to multiply that by 3n. So if we wrap that in a big O, so big O of f of n, is going to give us big O of n to the fourth, because n to the fourth is the dominant term in our function f of n. There's some other classic examples of big O. So if we have to find all the subsets of a set, that takes an exponential amount of time, because there are 2 to the n subsets. Finding all permutations of a string takes big O of n factorial. Another classic one is merge sort. So if we have n times log n for your merge sort. And if we have to iterate over all the cells of an array of size n by m, we have big O of nm time.
So what is ClickUp? ClickUp is an all-in-one productivity software where you can manage everything in n.
All right, let's talk about arrays. Probably the most used data structure. This is part 1 of 2 in the array videos. The reason the array is used so much is because it forms a fundamental building block for all other data structures. So we end up seeing it everywhere. With arrays and pointers alone, I'm pretty sure we can construct just about any data structure. So an outline for today's video. First, we're going to begin by having a discussion about arrays and answer some fundamental questions such as what, where, and how are arrays used. Next, I will explain the basic structure of an array and the common operations we are able to perform on them. Lastly, we will go over some complexity analysis and look at some source code on how to construct a dynamic array using only static arrays. Discussion and examples. So what is a static array? So a static array is a fixed length container containing n elements which are indexable, usually on the range of 0 inclusive to n-1 also inclusive. So a follow-up question is, well, what is meant by being indexable? So answer to this is, this means that each slot or index in the array can be referenced with a number. Furthermore, I would like to add that static arrays are given as contiguous chunks of memory, meaning that your chunk of memory doesn't look like a piece of Swiss cheese with a bunch of holes and gaps. It's contiguous. All the addresses are adjacent in your static array. Mm-hmm. Okay, so when and where is a static array used? Well, they're used everywhere, absolutely everywhere. It's hard to make a program that doesn't use them, in fact. Here are a few places you may or may not know that do use arrays. So, of course, the first simple example is to temporarily store objects. This is the most common use of arrays that you are probably familiar with. Next is that we use arrays as buffers to store information from an input or an output stream. Suppose you have a really large file, for instance, that you need to process, but that file is so big it doesn't fit it all in memory. So we use a buffer to read small chunks of the file into the buffer or the array one at a time, and so eventually we're able to read the entire file. I also like to use arrays as lookup tables because of their indexing property. So this is a really easy way to retrieve data from a lookup table if you know where everything is and it's supposed to be and at what offset. Next, we can also use arrays as a workaround in a programming language that only allows one return value. So the hack we use then is to return a pointer or a reference to an array, which then contains all the return values that we want. This last example is a bit more advanced, but arrays are heavily used in a programming technique called dynamic programming, with tabulation to cache already computed subproblems. So a classic example of this might be the knapsack problem or the coin change problem. All right, time to talk about some complexity. So the access time for a static array and a dynamic array is constant because of the property that arrays are indexable. So searching, however, can take up to linear time because we potentially have to traverse all the elements in the array in the worst case, such as if the element you're looking for does not exist. Inserting, appending, and deletion from a static array doesn't really make sense. The static array is a fixed size container. It cannot grow larger or smaller. When inserting with a dynamic array, this operation can cost up to linear time because you potentially have to shift all the elements to the right and recopy all the elements into the new static array. This is assuming we're implementing a dynamic array using static arrays, however. Appending, though, is constant. Doesn't that seem a little strange? Well, when we append elements to a dynamic array, we have to resize the internal static array containing all those elements. But this happens so rarely that appending becomes constant time. Deletions are linear for the same reasons that insertions are linear. You have to shift all the elements over and potentially recopy everything into your static array. Okay, so we have a static array A I've defined at the top. So A contains the values 44, 12, -5, 17, 6, 0, 3, 9, 100. Currently all the elements are distinct, but this is not a requirement of an array. Also remark that the very first element, 44, has index of position 0 in the array. Not 1. This confuses many intro computer science students who have no idea. The confusing part is that most, if not all, of mathematics is 1-based, while computer science is 1. Now, if we look at A, you can see that it contains the values 44, 12, -5, 17, 6, 0, 3, 9, and 100. Currently, all the elements are distinct. However, this is not at all a requirement of the array. Also remark that the very first element, 44, is indexed or positioned at index of 0 in the array. Not 1, 0. This confuses a lot of intro computer science students. The confusing part is that most, if not all, of mathematics is 1-based, while computer science is 0-based. This is what causes the confusion. But worst of all is quantum computing. I did research one summer in quantum computing during my undergrad, and the field is a mess. It tries to please mathematicians, computer scientists, and physicists all at the same time. And indexing just doesn't work well. Anyways, back to arrays. I should also note that the elements can be iterated over using a for each loop, something that's offered in some programming languages. It doesn't require you to explicitly reference the indices of your array, although the indexing is done internally, behind the scenes. The notation of the square brackets denotes indexing. So array A, square bracket 0, close square bracket is equal to 44, meaning A at position 0 is equal to the value 44. Similarly, A at position 1 is 12, A at 4 is 6, A at 7 is 9. But A at index 9 is out of bounds, and our program will throw an exception. Unless you're in C, it doesn't always throw an exception, unfortunately. Okay, now if we assign position 0 to be -1, that happens. If we assign index 5 to be 18, and if we assign index 6 to be 25. Let's look at operations on dynamic arrays. So dynamic arrays can grow and shrink in size as needed. So the dynamic array can do all the similar get set operations static arrays can do, but unlike the static array, it grows in size dynamically as needed. So if we have A containing 34 and 4, then if we add -7, it gets appended to the end. If we add 34 again, then it'll add it to the end. And we can also remove elements. So you see here our dynamic array shrink in size. Pretty cool, right? Okay, so we already talked about this a little bit, but how do we formally implement a dynamic array? Well, the answer is typically this is done with a static array, but this is not the only way, of course. So first we create a static array with some initial capacity, usually non-zero. So as we add elements to the underlying static array, keeping track of the number of elements added. Once we have to add an element which exceeds the capacity of our internal static array, what we can do is we can double the size, copy all the elements into this new static array, and add the new element we need to add. Let's see an example. So suppose we create a dynamic array with an initial capacity of 2. Then we begin
Finding a way to combine all my skills was always a little overwhelming, but now it's a lot easier and more fun with Skillshare.
adding elements to it. So the little circle with the slash through it is a placeholder for an empty position. Okay, so we add 7, everything's fine. We add 9, everything's fine. But once we add 3, it doesn't fit in our internal static array. So we double the size of the array, copy all the elements in, and now we can add 3. Now if we add 12, everything's still okay. We're doing good. And if we add 5, okay, we have to do a resize again. So double the size of the container, copy all the old elements into this new larger array, and then finish off by adding 5. And similarly, we can add 6 without any issues. All right, time to look at the dynamic array source code. This is part 2 of 2 in the array series. So the source code for this video can be found at the following link, github.com/myusername/data-structures. Also make sure you saw the last video so you know what's going on with this array implementation. All right, here we are in the array class. So I've designed an array class to support generics of type T. So whatever type of data we want in this array, that's fine. So here are our 3 instance variables that we care about. R, which is our internal static array. Len, which is the length the user thinks the array is. And capacity is the length of the actual array.
Alrighty.
Because sometimes our array might have more free slots, and we don't want to tell the user that there's extra free slots that are available. That's just our internal knowledge. So there's 2 constructors. The first one will initialize the array to be of size 16. The other one, you give it a capacity. The capacity, of course, has to be greater than or equal to 0. And then we initialize our array and cast it to a type T. Also notice I need to put this suppress warnings unchecked just because of annoying generics in Java. So here are 2 simple methods: size, get the size of the array, and check if the array is empty. Pretty self-explanatory. Similarly, for get and set, we just index into the array if we want the value, or set it if we want to set the value. Technically, I should be doing a bounds check for both of these, but I'm not, apparently. Okay, clear. So here we just remove all the data in our array and reset the length. Simple. This next one is the add method, where things actually get a little bit more complicated. So this condition says, hey, if the length plus 1 is greater than or equal to the capacity, then it's time to resize my array. The way I'm resizing is I'm doubling the size of the static array. You don't have to double the size, but I've decided that doubling the size is convenient. So when I double the size, I have to create a new array with a new capacity, copy everything in. This is what this line or these lines are doing. It's copying the old values back into this new array, and then it sets the old array to be the new array. And lastly, here we just copy the new value into our array. So this remove as method will remove a particular value at a given index. First, we check if the index is valid. If it's not, throw index out of bounds exception. Otherwise, grab the data at the remove index, initialize a new array of size length -1. Now copy everything into the new array except for when it's at that remove index. Now I'm sure there's easier ways to do this, but I decided to do the following. Maintain 2 indices, I and j. Increment I and j as you go, but when I is equal to the remove index, then we skip over the remove index by fixing j temporarily and using j to lag behind, if you will, while I is still in the original array. So I guess pretty clever overall. And then set the array to be the new array we just generated, reset the capacity, and return the data we have just removed. So this next one, remove, we scan through the array. If we find the object we're looking for, remove it at the index and return true, otherwise return false. Index of is very similar. If you find it, return I, otherwise return -1. Contains just checks if index of is not equal to -1. All right, this next one, I return an iterator for the array. So an iterator allows us to iterate over the array, providing an abstraction for it. So I need to override two methods, and this is has next. So there exists the next element in our array if the index is less than the length of the array. I should also be
Just
checking for concurrent
methods.
modification here, just in case someone decides to change the array for some reason while we're modifying it.
Plus, he does have to.
We might add that later, might not. Also, there's the next method, which just returns the next element in the array relative to the iterator. Okay, and lastly is the toString to get a string representation of this array. Nothing too complicated. All right, so this is a very simple data structure. It's just a dynamic array. If you look at Java's array list, it looks very, very similar to this. Today, we're going to
Hey, Fidelity. How can I remember to invest every month?
With the
talk about singly and doubly linked lists, one of the most useful data structures out there. This is part 1 of 2. In the second part, we will be looking at some source code on how to implement a doubly linked list. So for today's outline, in the first section, we're going to answer some basic questions concerning singly and doubly linked lists, namely what are they and where are they used. Next, we're going to cover some terminology concerning linked lists so everyone knows what I mean when I say the head of the linked list versus the tail of the linked list. Then last in the discussion, we'll talk about the pros and cons of using singly and doubly linked lists, then how to insert and remove elements from both singly and doubly linked lists, as well as some source code. So stay tuned. All right, discussion. So what is a linked list? Linked list is a sequential list of nodes that hold data which point to other nodes also containing data. So below is an example of a singly linked list containing some arbitrary data. Notice that every node has a pointer to the next node. Also notice that the last node points to null, meaning that there are no more nodes at this point. The last node always has a null reference to the next node. For simplicity, I will omit this in the following slides. Okay, so where are linked lists used? One of the places they get used the most is actually in the abstract data type implementation of lists, stacks, and queues because of their great time complexity for adding and removing elements. You also see linked lists in things like circular lists, making the pointer of the last node point to the first node. So circular linked lists are used to model repeating event cycles, maybe like having a round robin ordering on a bunch of elements or representing corners of a polygon. So definitely a lot of uses there. Linked lists can also be used to model real world objects, such as a line of train carts. That could be useful. And moving on to some more advanced examples, we also heavily use linked lists in hash table separate chaining and for adjacency lists in graphs. We'll get to those in a later video. Okay, a bit of terminology surrounding linked lists. First thing you need to know when creating a linked list is that we always maintain a reference to the head of the linked list. This is because we need somewhere to start when traversing our list. We give a name to the last element of the linked list also. This is called the tail of the list. Then there are also the nodes themselves, which contain pointers. Pointers are also sometimes called references, and these pointers always point to the next node. You should also know that the nodes themselves are usually represented as structs or classes when actually implemented. We'll get to this when we look at the source code. Okay, singly versus doubly linked lists. So concerning the kinds of linked lists that there are two types, singly linked and doubly linked. Singly linked lists only contain a pointer to the next node, while doubly linked lists not only contain a pointer to the next node, but also to the previous node, which makes it quite useful sometimes. This is not to say we cannot have triply or quadruply linked lists, I just wouldn't know where to place the additional pointers. Pros and cons of doubly linked lists. So there are trade-offs between picking a singly and a doubly linked list. What are they? If we look at the singly linked list, we observe that it uses less memory. Why? Well, pointers to nodes can actually take up a lot of memory. If you're running on a 64-bit machine, references use 8 bytes. On a 32-bit machine, 4 bytes each. So having a singly linked list means you only need one pointer for each node, hence twice as much memory is saved. A downside, however, is that you cannot access previous elements because you don't have access to them. You would need to traverse from the head of the linked list all the way up to the previous node to find it. Now, concerning doubly linked lists, well, a great pro is that having access to the tail, we can easily traverse the list backwards, something we can't do with a singly linked list. Also, having a reference to a node you want to remove, you can remove it in constant time and patch the hole you just created because you have, again, access to both the previous and the next nodes. This is something you cannot do with a singly linked list. You would leave the list severed in two. A downside, however, to the doubly linked list is it does use up twice as much memory. Okay, let's go into some implementation details on how we can create linked lists and remove elements from linked lists. Starting with singly linked lists. So here is a singly linked list. I've outlined where the head and the tail is. Now we want to insert 11 at the third position, where 7 is currently. Let's walk through an example. So the first thing we do is we create a new pointer, which points to the head. This is almost always the first step in all linked list operations. Now what we're going to do is seek up to, but not including, the node we want to remove. So if we seek ahead, we advance our traversor pointer, setting it equal to 5's next node, which is now 23. And now we're actually already where we need to be to insert the next node. So we create the next node, that's the green node, 11. And we make 11's next pointer point to 7. And the next step is to change 23's next pointer to be 11. Remember, we have access to 23's next pointer because we have a reference to it with the traverser. Okay, and now if we flatten out the list, we can see that we've correctly inserted 11 at the right position. And we're done. Okay, all right, time to insert with a doubly linked list. This is much trickier because of all the pointers flying around, but it's the exact same concept. Notice that a doubly linked list not only has pointers to the next node, but also to the previous node. We also have to change those in the insertion phase. Okay, create a traverser pointer, which points to where the head is, and advance it until you are just before the insertion position. So we advance the traverser by 1, and now we're just before the node, so we stop traversing. Let's create the new node, which is node 11. Point 11's next pointer to equal 7. Also point 11's previous pointer to be 23, which we have a handle on because of the traverser. Now, we make 7's previous pointer equal to 11, so we can go backwards from 7 to 11. And the last step, make 23's next pointer equal to 11. This is so that we can go forwards from 23 to 11. So in total, remark that we changed exactly 4 pointers. So if we flatten out the list, you can see that 11 has been inserted in the correct position. All right, now how to remove elements from a singly linked list. So suppose we want to remove the node with a value 9. How do we do this? Well, the trick we're going to use is not to use 1 pointer, but 2. You can use 1, but for visual effects, it's easier to show you how it is done by using 2. So we create pointers trav1 and trav2 for traverser 1 and traverser 2, respectively. So traverser 1 points to the head. Traverser 2 points to the head's next node. Now what we're going to do is advance trav2 until we find the node we want to remove, while also advancing trav1. Okay, we have found node 9, so this is the stopping point. I'm going to create another pointer to the node we wish to remove, so we can deallocate its memory later. Okay, so now I have advanced trav2 to the next node, and node 9 has turned red. I've done this to indicate that at this point, node 9 is ready to be removed. I'm just keeping it around for the visual effect. Okay, so now set trav1's next pointer to be equal to trav2. And now it is an appropriate time to remove the temporary pointer because we're doing nothing with it. And there, temp has been deallocated. Make sure you always clean up your memory to avoid memory leaks. This is especially important in C and C++, and other programming languages where you manage your memory. Now you can see that 9 is gone, and our singly linked list is shorter. Okay, now for the last bit of implementation, let's look at how to remove nodes from a doubly linked list, which is actually easier, in my opinion, to removing from singly linked lists. The idea is the same. We seek up to the node we wish to remove, but this time we only need 1 pointer. One traverser pointer, because each node in the singly linked list has a reference to the last node, so we don't need to manually maintain it like we did with the singly linked list. So let's start trav at the very beginning and seek until we hit 9. Okay, we've reached 9, and we want to remove it from the list. To do this, set 4's pointer to be equal to 15. We have access to 4 and 15 because they are trav's previous and next pointer, respectively. Similarly, set 15's previous pointer to equal 4. Notice that trav is now red, meaning it is ready to be removed. So we get rid of trav, and now if we flatten out the doubly linked list, we see that it no longer contains 9. Let's do a bit of complexity analysis on linked lists. How good actually are linked lists? On the left column, we have singly linked lists, and on the right, doubly linked lists. The complexity for searching in a linked list is linear, in the worst case, because if the element we're looking for is not there, we have to traverse all of the n elements. Inserting at the head, though, is constant time, because we always maintain a pointer to the head for a linked list, and hence we can add it in constant time. Similarly for the tail. To remove the head of a singly linked list and a doubly linked list is also constant time, again, because we have a reference to it, so we can just remove it and advance the head by 1. However, removing from the tail is another story. It takes linear time to remove elements from a singly linked list. Can you think of why? Well, even if we do have a reference to the tail in a singly linked list, we can remove it, but only once, because we can't reset the value of what the tail is. So we have to seek to the end of the list and find out what the new tail is equal to. Doubly linked lists, however, do not have this problem. since they have a pointer to the previous node. So we can continually remove nodes from the tail. And finally, removing somewhere in the middle is also linear time, because in the worst case, we would need to seek through n-1 elements, which is linear. All right.
Full Sail University is where you can get hands-on experience with emerging technologies.
Okay, time to look at some doubly linked list source code. This is part 2 of 2 in the linked list series. So the link for the source code can be found on GitHub at github.com/williamfisa/data-structures.
I don't see. There we go. Linked list. Wow, he codes out everything.
Please start this repository if you find the source code helpful so that others may also find it. And also make sure you watch the first part of the linked list series before continuing. Here we are in the source code. We're looking at the implementation of a doubly linked list in Java. So first, notice that I have declared a few instance variables. So we are keeping track of the size of the linked list, as well as what the head and the tail currently are. To begin with, the head and the tail are null, meaning linked list is empty. Furthermore, we will be using this internal node class quite excessively because it contains the data for our nodes, and it also contains previous and next pointers for each node, since this is a doubly linked list. So we have one constructor for the node, namely the data and the previous and the next pointers themselves. We need both, otherwise we can't do much. So this first method I have declared here is to clear the list. It does so in linear time by going through all the elements and deallocating them one at a time. It deallocates them by setting them equal to null. So we start a traverser at the head, we loop while the traverser is not equal to null, meaning there are still elements in the list, and then we do our deallocation business. And at the end, we set the size equal to 0 and reset the head and the tail. Perfect. These size and empty methods are pretty self-explanatory. Get the size and check if the size of our linked list is empty. Okay, so here I have a public method to add an element. By default, we're going to append to the end of the linked list or at the tail. But I also support adding to the beginning of the linked list. So how we do this? If this is the first element, aka the list is empty, then we set the head and the tail to be equal to the new node, which has, as you can see here, both previous and next pointers set to null. Otherwise, if the list is not empty, then we say the head's previous pointer is equal to this new node, and then we set the head pointer to be whatever head's previous is. So we back up the pointer in a sense, and we also don't forget to increment the size. A very similar thing is done when we want to add to the tail of the linked list, except we're moving the tail pointer around. Okay, let's move.
I honestly don't think I can sit and watch the next part. So, man, brain freezing. We basically create the whole class. Is great, and then he also did it in C++. Cool.
Move to peak.
What I'll do is stop here for today and pick this up tomorrow. I have to go through this whole series. Anyway, so yeah, cool. See you guys tomorrow.